Good morning for everyone. I am really happy to be here today. We start a new series of the Cine webinars for 2022. And then this year is a special year for us because we are looking for a very nice, very respectable scientist to start this series of the webinars. And today, we have the pleasure to have here today Professor Nicholas Kotov. Just would like to invite him for the stage. And before I start his talk, I would like to say a few words about himself. First of all, for everyone in this audience, when you are looking to start to see this talk in future too, just look at his Google Scholar, just for you to see with who you are talking about. And from the papers that you have published in the last 20, 30 years, you're going to see how much remarkable his achievements. After that, I will ask for you to see his page, his profile page, when you see his profile, his story there. When he tells about how he starts on the nano, to have his interest on the nano science, how he started as a scientist, I was very impressed to read it. When he mentioned that he started his, let's say, scientific career at 7 years old, doing some artwork, which is very impressive, and tells us is how is a scientist, how we start. And the most important is how he keep his motivation doing that high quality science for so many years. This is so impressive for the young generation that we should learn it. And beyond of that, he find time to be a very distinguishable professor in the University of Michigan, where he's studied for many years, and went through several different institutions in where he provided his contribution. And also he's now leading his department in the Michigan University. And beyond of that, he also has a contribution for the society when he opened, several startups from the contribution. When these startups have a direct contribution for the society, it's a returning for how to improve our society, which it makes us very happy, because today there's a lot of concerns how to translate the knowledge that we generate inside of the universities to the society. And this is an example how you can do it. And then today, Professor Nicholas Kotov is going to talk about nanostructures, how his curial nanostructures. This is a very exciting topic. That is, we can learn a lot of things, and beyond of that, it can be used for a large number of applications when it can be manipulated and controlled in a nice way. And he's going to tell us how to do that. Nicholas, we are very happy to have you here with us. Okay, thanks. Okay, the stage belongs to you now.
Thank you so much. It's really a great honor to have that introduction. And it's also an honor to be part of this event. This work on chiral nanostructures is done in collaboration with many scientists, including the scientists, very exceptional scientists from Brazil. And speaking of the international collaborations, and speaking of what to me to be a scientist, it's actually to speak the truth all the time. And in that respect, I would like to say that a lot of our colleagues in Ukraine have been displaced, they suffer, they have been brutally assaulted by a big army, by the army of the country which I was a part of. And this is extremely shameful. And I would like to call for everybody to stand with Ukraine and to stand with the colleagues there. Back to the content of the research, because eventually This is what drives us all to be excited about the research and to see its implementations. And I think that chiral nanostructures offer that in multiple ways. In this talk, I would like to highlight the novelty of inorganic chiral structures and show you where we can have a big distinction between the old chiral structures and the new one. I would also like to relate the chirality and complexity. And through that, I would like to also to show you some of the applications in catalysis, which directly relates to the energy applications, and biomedical applications, which are related to the fight against the viruses. There are many groups that are working in the world on chiral nanometer scale structures. And the motivations can be very different, but for the majority of us, high optical activity of the inorganic nanometer scale structures is the key. There are also some other reasons, for instance, high complexity assemblies and the convergence of the inorganic materials and biological materials, with chirality being an essential property for both sides. I'll start with high optical activity and explain where does it come from. The geometries in organic structures, which are chiral, and the geometry of inorganic structures are actually quite the same. For example, we can have the tetrahedral structures made from nanoparticles, or helical structures from carbon sheets, or these twisted rods structures, and later you will see the repellers. If we look at the foundational properties of the materials which polarize light, we can relate the intensity of circular polarization with a parameter called rotatory strength, which is the imaginary part of the dot product between the transient electric dipole and transient magnetic dipole. You can imagine the transient electric and magnetic dipole as the polarization of the molecule or any other structure as it absorbs or emits light. Let's look at the transient electric dipole because it's a little bit easier, but all the derivations are actually valid for transient magnetic dipoles. If we look at where does it come from, it is proportional to the square root of dynamic polarizability. And the organic materials have quite low dynamic polarizability, but semiconductors and metals have multiple orders of magnitude higher dynamic polarizability. And for that reason, if we take the square root, we have at least 3 order of magnitude enhancement of the rotatory strength. For the first time, it was observed for the assemblies of gold nanoparticles, which are interconnected by molecular strands. And if you can see here in the near infrared part of the spectrum very strong peaks, which are associated with the absorption of light in these carbon structures, which are made from gold nanometer scale particles. It was off the chart at that time, and later on, we used the fact that it is located in infrared and very strong for a number of applications, and in particularly for the analysis of DNA. It was done with my good colleague in China, with Professor Chuanlai Xu. And initially, we had achieved the attomolar detection of DNA. Again, this is due to the fact that it's not only intense, it is intense, but also it is located in the part of the spectrum characteristic of gold plasmons. And in this part of the spectrum, there is a little noise. And later on, we could also achieve even the zepta molar detection of DNA, which was not possible to achieve by other means in the same field. And nowadays, this work is being translated to multiple venues, including the detection of Au-Cys. If we look at other parts of the motivation, I would like to highlight the fact that we want to form highly complex structures, and methods to assemble them is quite important and interesting for many different parts of the technologies. We want to make the hierarchical materials, for instance, for the replacement of bone. It's very structured, it has multiple components, and it's all made in nature by self-assembly. Also, we can look at the complex structures which are made in thylakoid membranes for light energy conversion. The question now is how to make these structures and make it easy. So some of the ideas in these areas were put forward by Professor Murray Gell-Mann. He received the Nobel Prize for the discovery of quarks, and later in his career, he started thinking about what complexity means. And he introduced a notion of effective complexity, or the functional complexity, which is related to the complexity which is needed to achieve a specific biological functionality. It turns out that complexity, if we look at the ordered structures and disordered structures, is low. And the functional complexity needs to have some amount of disorder and some amount of order. With that idea and self-assembly of the nanoparticles in mind, we started looking at the possibility to form the complex assemblies from the simple nanometer scale particles. We know that they can self-assemble, for instance, in particle chains. These are fairly simple and certainly functional. It's being used in multiple technologies now to conduct electricity or to store electrons in batteries. But let's try to make some more complex, more functional structures. And in that way, we have a number of problems. First, every nanoparticle every type of nanoparticles have some polydispersity. And the question is whether that distribution of sizes, shapes, and composition is actually not too high in order to get to a disorganization part of this Gaussian curve. The other part is related to thermodynamics. It turns out that the highly complex assemblies are actually have higher in energy than, say, disorganized structures. If we look at the nanoparticles, some random agglomerates or these high mass states, they're not complex, but they are resulting from strong interactions and in multiple directions, and this results in the reduction of energy. So how do we get to this part of the thermodynamic landscape? In the past, we learned that we can actually restrict self-assembly by introducing some repulsive interactions. So we have to find some methods, some pathways which involve not allowing these high mass assemblies to form. And it can be done, at least in some instances, for instance, for the formation of supraparticles. They are made from a large number of very dispersed nanometer scale particles, and yet they form quite uniform sized particles, which by and large are reminiscent of micelles. The reason for that is that the electrostatic repulsion of new particles, which might want to join the supraparticles, is too high in order for them to overcome this barrier. And this is true specifically for nanoparticle assemblies in water because they all have very high charge. If we try to replicate it for some more complex structures, the role of chirality may be very useful because from biology we know that the chirality and complexity are connected. And thus we started making the particles of about the same size in single nanometer range, which are chiral. And this was done initially with gold sulfide sheets, which are coated with histine on top and the bottom. This work is done in collaboration with Professor Andrea de Moura from the University of São Carlos. And as you can see, the dispersity here is very high, and yet we learned that these particles can produce very complex assemblies. So we saw that if we have L-cysteine, the stabilized gold nanosheets, they form the hedgehog-like particles with, again, a uniform size. That uniformity is a very good indication of that self-limited assembly restricted by electrostatics that we previously investigated with my other collaborator, Warren Glauser. If we make the particles which have mixed D and L, histine in equal amounts, we form also quite complex particles that can be referred to carbonic particles. If we change the chirality of cysteine to D, we saw that by and large, overall shape and size of the particles does not change, but where this change is profound is at the structure of the spikes. Every spike is actually an assembly of the nanosheets, which are twisted left or right, depending if we used L or G cysteine. And each nanosheet is actually stacked as a fan in the second order organizational pattern. So the uniformity of the nanoparticles is quite amazing. The supraparticles. And this can be appreciated from the scanning electron microscope. So we have very wide range of sizes of the individual building blocks of these nanosheets, but overall, once they assemble, the dispersity of these particles is very small. And that's because of this very firm restriction by electrostatic forces, which is a thermodynamically defined particle size. If we vary the composition of LNG cysteine, so if we vary the chirality parameter of the system, we will change the composition and the structure of the particles in a very wide range. So here you see the phase diagram, which contains many different particles. And for instance, we can have here supraparticles from the nanosheets, or this twisted bundles, or the star-like particles from these twisted sheets, and of course, supraparticles from supraparticles. The chiral hedgehogs are here, and the kayak particles are here. Now the question is, which of these particles are more complex? And in order to answer this question, we spent about a year and a half just looking for the right methodology. And it turns out that graph theory offers the most universal and the most accurate assessment of the complexity of the chemical structures. For the folks who have not looked in it in the past, a graph is actually a fairly simple to understand structure. It's a set of nodes and edges. So we can have nodes and connect them or not with edges, and that would be a general graph. Complexity is very inherent to the graph theory because this field of science encompassing many different other fields of research for instance, the social sciences, as well as the computer sciences, and complexity has been used in this field for quite some time. We can use multiple evaluators of complexity. For example, we can use the multifractal parameters. We're working on that with our good collaborator, Paul Bogdan. We can also use the connectivity index, which is describing how intricate are the connections between nodes and edges. And also, we can use complexity index, which was in the past introduced in chemistry by Randic and Plavich, and we extended it to semi-infinite structures in the nanometer scale realm. So complexity index enables us with this modification to assign the value of complexity to these chains that you saw before, or to the stacks of nanorods, or to the nacre-like stacks of the nanosheets from any different materials, from graphene or from real nacre, or to the supraparticles and superlattices that you saw. So how to do this? It's actually quite simple. We can define a nanoparticle which, for instance, has a random shape or isotropic shape, for instance, the sphere, or in sometimes the cube, as a node. And if they are connected, and the connection is normally done by organic layer, that would be an edge. And with that, we can expand this idea to a variety of nanometer scale assemblies and structures. The key attribute of that step of expansion would be to introduce additional descriptors for nanoparticles, nanostructures, which may actually have an isotropic shape. For instance, rods can be described in a minimal way by a pair of particles, a K2 graph. A sheet is 3 particles. Define the sheet. It will be a K3 graph. Chiral nanostructures, or chiral structures in general, are described by this K5 graph. This is again a minimal representation of the three-dimensional chiral structures. The same rules apply, so if they are connected, we will use the organic locations of the connectors as edges. So now we have a very universal toolbox that we can apply to a variety of complex assemblies from the nanometer scale structures from any material. So let's make a check if we actually calculate the chirality index, and it's calculated in this way. Correctly, and it correctly represents our perceived complexity of the structures. So this is the pair. The complexity index is higher than individual particle, which is certainly true, and its complexity index is 1.5. If this structure is chiral, for instance, a twisted ribbon structure, we have immediate rise of complexity to 12. If the particles form chains, as they often do, we can see that it should be higher than a pair, but maybe lower than the twisted ribbon. If we calculate, it is indeed correct. It's 6, somewhere in between. The reason why it shouldn't be too high, because the pattern here is still the same. So the idea of complexity is how diverse are the rules which are embedded in the structure. And we can extend it to some other more complex systems, for instance, nacre-like structures or supraparticles. They're both made of nanosheets. In this case, they are randomly distributed. In this case, the nanosheets are stacked. So in principle, there are more rules here. And if we calculate the complexity index for supraparticles from sheets, it is 6. And for nacre, it is 24. I'd like to point out that this structure of nacre is actually very functional. And indeed, if we look at the technology, there are many different materials which are used now, which have the two-dimensional architecture of stacked sheets and the variety of functional properties which are associated with this fairly high complexity index is actually quite amazing. Which confirms the diagram of functional complexity having a certain amount of order, but a certain amount of disorder as well. So now, when we are confident in the meaning of complexity index, we can calculate it for kayak particles. You can see here the nanosheets, they're connected. This is supraparticle-like parts here. And the coral hedgehogs that have this the nanosheets which are twisted. These are these pentagons, and they're stacked. So these are the assemblies, and all together they form a supraparticle. So complexity index here is 87, very high. What we also learned that it's not only higher than some other assemblies that we form, but also it is higher than the prototype that we saw in the nature. These are the vocalists, or the skeletons of some algae. And if we apply the same stringent rules to establish the complexity index of Au-Cys skeleton, we can see it's actually 49. It might give you a pause, as it gave me, because it means that in the lab, we actually form a more complex structure than the nature did. And after some consideration, it's actually not surprising because we actually have done it many times in the past. And the nacre sheets and the nacre-like materials are now actually more complex, more sophisticated, having multiple stratified layer of different materials than the actual nacre. The graph theory can also be applied to some other particles and some other materials in the same exact way. And we can look at the complexity indices of some other unusual, sophisticated particles, for instance, used in absorption of gases or catalysis or optics. And we can create the graph theory structure of these particles, and in a way, these are analogs of the molecular structures which are used in chemistry and calculate their complexity index. What is very useful about these structures is because now we have a way to encode that architecture in the nanoscale formulas. And having those, we now can apply a variety of tools for instance, the machine learning in order to engineer them. In fact, by using the indices and the structure, we can have now the mathematical toolbox in order to say we want these properties and we want that structure in order to accomplish it. Now, let's address the question of the relationship between chirality and complexity, which is quite fundamental to this field and others. And we can map onto this phase diagram the complexity diagram. So these are complexity indices which were calculated for each of the structures. And you see the graph theoretical representations of those. The chiral hedgehogs are definitely the maximum, and they have the maximum chirality coordinate. But in the same time, you can see that there are some very complex structures which have fairly low chirality, and in the same way, there are chemical structures which have the highest chirality and that are not complex. The same message, the same point can be made in some other experiment. For instance, if we add a chiral thioglycolic acid to the preparation of the viral hedgehogs based on L-cysteine, and we can see non-linear dependence of complexity and chirality. So as soon as we add a little bit of thioglycolic acid, the complexity drops. We only have this ugly high mass agglomerate that we try to avoid. But then as we add a little more, we see increase of complexity and the formation of supraparticles, and then it drops again. And then we recover some amount of complexity. So how does it fit in our understanding of engineering of complex systems? To make the long story short, complexity, as you see, does depend on chirality, but this dependence is non-linear. And the reason for non-linearity is because chirality is not the direct parameter which relates to complexity. Complexity comes actually from the competition of restrictions. And electrostatic restriction and some mechanical restrictions, some hydrogen bonding restrictions, they all produce these complex structures. So if we want to point it out, complexity is related to competition and diversity of the forces and particles which are involved. I might want to highlight this point in another way, that for nanoparticles, in order to make complex structures, the monodispersity is not required at all, as you could see. And in fact, the polydispersity or diversity is needed. And actually, this is not the same in biology. Of course, there are very good examples of complex and structures which are made from a very wide range of components. But if we look at the same kind of scale and the same hierarchical structures formed, for instance, by molecules, amyloid peptides, or protein sheets, or the viruses, which are supraparticles, we see that in most cases, these assemblies need actually specific molecular organization, and the polydispersity is low. And that's because the requirements for strong attraction for these structures is based on the specific molecular architecture. For nanoparticles, that requirement is relaxed. Now let me address the utility of complex systems. For the hedgehogs, it can be demonstrated quite easily because they acquire very new properties. For example, if we have this architecture of the particles, we see not only very strong optical activity, but also a new property, which is omnidispersity. So these are hydrophilic particles, and yet they are dispersed in water, in ethanol, and DMSO, and even in one of the iconic solvents in hydrophobic range, the toluene. We found it for non-chiral particles, which are made from zinc oxide, and established that this property is specific to this rigid spikes, which reduce the van der Waals interactions by about 2 orders of the magnitude. The optical properties are also the consequence of complexity. For example, we were very happy to see a very strong and very unique set of circular dichroism bands in the chiral hedgehogs, as well as the circularly polarized light emission. And we found that this band, which is related to the very useful infrared part, is directly related to this complex architecture of the particle, as can be demonstrated by molecular models. So if we split these particles into simple spikes, this band disappears. Another pathway to demonstrate the usefulness of complex structures lies through catalysis. And you can see that it is an important field, and I don't need to highlight the achievements of many scientists that you see here in the past. And looking and search for new chiral catalysts is quite relevant for even now for a number of areas of energy and green technology. So one of the hard reactions is actually formation of CC bonds. And to make it in a chiral fashion is even more complex. And one of the typical reactions here, which have been investigated by marvelous scientists, equally decorated as the ones before, but it's very actually hard. In order to carry out these reactions, people use the homogeneous catalysts, which are expensive, based on organometallics, metals, and it's normally carried out equally expensive organic solvents, and the enantiomeric excess is actually quite low. So now let's try to replicate that reaction in supraparticles. We want to have aqueous solvents, very inexpensive viral catalysts, which are also stable. So we decided to engineer the complex particles made from gold nanoparticles and zinc sulfide chiral nanoparticles, which are stabilized by L or D penicillamine. The complexity index here is again fairly high, and as you remember, if we get to this range, it's already becoming very functional. And we looked at the photocatalysis of tryptophan and tyrosine. We found that for photooxidation of tyrosine, gold particles here absorb light, transfer excitation to zinc sulfide, which carries out the C bond coupling reaction. The yield of tyrosine for these complex supraparticles is higher than for the nanoparticles. The enantiomeric excess is higher than for nanoparticles and is actually higher than the previous examples of that you saw before for expensive organometallic catalysts. We see the enantiomeric excess in the range of 30%. The stability is also high. So for the catalyst, it's very difficult to protect the particle against the ultraviolet photons. Supraparticles are much more stable, as you can see here by these pink lines, than individual nanoparticles that degrade. So that is indication that we need to engineer the complex systems in order to create these functions. Of course, this assembly brings out a number of other interesting lines of thoughts. For example, if we can use the same principles to replicate some biological catalytic centers which carry out very difficult reactions. For example, the reduction of CO2 by light into some chiral materials, for example, sugars. These assemblies are replicating the function and complexity of the prototypes carboxysomes, but certainly they are built from a different, much more technologically friendly materials, such as the inorganic nanoparticles, which have high stability. They can be dispersed in water and still retain high catalytic activity. Now, I would like to address the part which is related to biomimetic nanometer scale structures. The complex materials and the complex nanoscale assemblies are visually functional uh, um, in that realm as well. So again, in collaboration with Professor Xu and Professor Maura, we investigated the chiral gold nanoparticles, which can gradually change the chirality due to the light-induced reduction of gold. We use here chiral light, and as we illuminate with circularly polarized light, we gradually increase the chirality of these particles from 0 to some high values, which can be enumerated by a number of chirality measures. And this tuning of chirality is very useful to answer the fundamental question whether the chirality of the particles can be used to induce some biological responses, and how does the chirality at nanometer scale relates to their biological functionalities. So we created a number of these chiral particles along the way. So we illuminated them for a different amount of time. And we saw a gradual increase of circular dichroism and the gradual increase of the G factor, which is a measure of optical asymmetry. It turns out that these particles can be also used not only for optical needs or for some other needs, but also as adjuvant for immune response. We hypothesized that the particles with different chirality will be recognized as cells in a different way. And I would like to highlight the fact that these particles have the nanometer scale chirality only after the formation, because all the molecular scale chirality had been removed by the change of the surface ligands of the particles. And it turns out that the induction of the immune response by exposure of the chiral particles to bone dendritic cells varies very strongly depending on the chirality of these particles. So if we look at the induction of the immune response, but very traditional antigen bioalbumin, we can see that left-handed particles induce the highest immune response. The right-handed particles induced it too, and the chiral particles, so the starting prism with very simple shape, they actually induce the smallest response in this way as the adjuvants. Importantly, here we see the gradual increase of the immune response and the chirality of the nanoparticles. This is a great indication that nanoscale chirality matters a lot to the recognition that happens between, say, antigens and cells, and we can harness that property or that math, if you want, that geometrical qualities, and engineer the nanoparticles in order to enhance it. Albumin is a fairly traditional antigen, and we decided to take the next step and to use H9N2 influenza virus. this work had started about 4 years ago, and certainly nowadays we would have started with coronavirus, but at that time it was not such a universal threat. And for this virus, we also found the same finding that L or left-handed particles have greater immune response or stimulate a greater immune response as an adjuvant, but it also stimulates greater immune response than the traditional adjuvants. The chirality and immune response are inherently connected here as well. With this, I would like to extend my great thanks to an amazing group of people who I have an honor to represent here at this webinar. These are my students and postdocs who you see in this slide. They are most hardworking and very insightful young people, and it's a pleasure to be a part of this community. I'd also like to thank the sponsors who you see over here. This is the Vannevar Bush Fellowship, the Newton Award, and other funding from URI and Air Force. Thank you so much, and I'll be delighted to answer any questions that you may have. Thank you.
First of all, I'd like to thank you for a very grateful and to say very insightful talk inside of the complexity. Try to make it simple, in fact. It's really great. We want to have a long discussion. We have some questions here. I think the first one, Marcelo, is from Pablo Sebastian. Can you just pick up it? So you can read the question there. I'm not going to repeat it because it's...
I do not see the question. If you could help me.
Marcelo. Okay. You basically from Pablo Sebastian Fernandes. He's a faculty member from Unicamp. He said, great talk, Professor Kotov. You showed a method to quantify complexity. What is the importance of this quantification apart from the academic interest?
Yeah, good question, and love this question. Please bring hard questions because they are good. And even if I don't know the answer, just thinking with you, it will stimulate science. Answering your question is, I would answer your question in this way. So it's not just academic, it's engineering. So if we look at the graph theory and its applications to the nanometer scale structure, I can bring this slide. It's a tool which is analogous to what we use now in chemistry to describe the structure of molecules. It used to be academic, but now it is actually a tool for industry and other sciences, of course. It codes the structure. It mathematically describes the structure in a simple concepts of nodes and edges. And it unifies the structural description between the chemistry and the nanometer scale science, because the tools are actually the same. The molecules are graphs. In here, we just introduce the difference between, say, the particles of the different anisotropy, and we can certainly introduce the difference in particles in terms of the materials. What you saw in the in the examples here, that, for instance, the particles with this geometry have unusual property and very specific to the geometry. So now we can go back and say, hey, I need the high dispersibility of particles in, say, hexane, or particles made of metal copper, or some semiconductor for supercapacitors. How do I create, and what structure of these particles is going to be? The graph theory will guide us into that.
Okay, thanks for the question. Now, I think Pablo put a second question too.
Yes,
Pablo.
Pablo.
Marcelo can take the second question. Basically, the second question means I love the synthesis of the Chiral gold nanoparticles using polarized light. With is the size of the spot. And,
the size of the spot of the laser. It's actually fairly big. So we use these particles for a number of reasons, for a number of applications, and we actually have created a fairly high throughput methodology for this synthesis. It's not we use not the original laser beam, which has very narrow spread, but we defocus the laser beam. It has the polarization, but defocusing enables us to cover a large volume of the reaction vessels. So the spot size is in centimeter range.
Okay, that's great. Okay, I have some few questions now. It's not few, but it's just one. You showed one slide when you put like a diagram, a 2D diagram. You show the chirality in the y-axis and the temperature in the horizontal axis.
Yeah.
And then you show that you are able to control the different shapes of the particles, not shape, but their complexity.
Yes.
And could you identify some additional parameter that you could, additional descriptor, physicochemical descriptor that you can use to control those systems, or the temperature and chirality are the most important ones?
Very good question. Yes. So chirality and temperature are not the only parameters which are essential for the particle shapes. The ionic strength is very significant, because ionic strength screens the electrostatic repulsion between the particles, and we saw very big change in the particle structure, architecture, assemblies when we add more salt. Basically, the tuning of the forces and thinking about how we can increase the competition, say, of electrostatic repulsion and the supramolecular attraction. So they have to be in the same range of energies, applies to the ionic strength as well. So we need to tune it in order to, say, have the right intensity of electrostatic repulsion. The other parameter here, which is essential, is the composition of gold material and gold sheets. So I mentioned a couple of times that the flexibility of these individual sheets that we start with matters. It creates this twisted structure. It also enables them to adapt to each other. and the competition between the mechanical forces and the electrostatic forces and supramolecular forces are all creates the complexity. We changed the composition of gold sheets by adding a little bit of copper and a little bit of silver. With addition of these ions, we change the rigidity of the sheets, because copper and silver can form more bonds, and this is different, and they have a different coordination number. And that creates a different structure of the particles. So the same diagram can also be made, for instance, for chirality and composition in terms of the metals.
Okay, that's great. Okay, just André Farias Moura, your collaborator here on the Federal University of São Carlos, is nearby to me here. He said, thank you for the very nice webinar, Nick. Always a pleasure to listen to you.
Okay. André, thank you. It's a pleasure to be collaborating with you. It's really a treasure to have your friendship and your insight in every work what we do.
Okay, great. The Federal University is just close to here in the São Carlos. One question I want to ask when you mentioned it is about the control of the electrostatic repulsion. Because to control the electrostatic repulsion, I imagine that you need to add some ligands on new molecules to create some the electrodelocalization towards the environment, because to enhance the electron density at that particular region, to enhance the electrostatic repulsion with the particles.
Yes.
Normally, what are the best ligands that you are going to put on those molecules, those systems, to enhance this electrostatic repulsion? Because it's not an easy task to control the electron density to save movement towards outside of the particle.
Again, another good hard question. So charges are extremely interesting part of these nanoscale systems. They are a part of long-range forces, and they actually have a number of contributors, and you already alluded to it. A part of it is electrostatic, a part of it electrodynamic. Some of them are dipoles, and some of them are ions, and some of them are electrons. So it's a very interesting conglomerate of different charged species. In fact, I'd like to point out that each nanoparticle is not only a charge like a macro ion, but also a dipole. So the control here, the simplest one, is to controlling the ligands which can ionize. So we often use some thiol acids. So sulfur atom is connected to the particle, and the acidic group carboxyl, it changes its charge in response to, say, pH of the media. In this way, you have a very firm, very universal tool how to control electrostatic restrictions here. And you can play with the ligands, say, to mix some ionizable ligands and some not very ionizable ligands, which do not have the carboxyl groups or have amine groups. So this creates a very wide range, an enormous range of the charged species that you can engineer here. And I use the word engineer in a very conscious way, because it is the level of molecular engineering of these complex structures which we have not yet achieved in the past in chemistry. So if we go a little bit further and ask, let's say, higher order electrostatic interactions, if we use the shape of the particles, that also creates very interesting electrical effects. The dipolar interactions can be very useful in order to create the twist. So if you, for instance, use the dipolar rod-like structures, then and just a slight bias, you can create a very uniform twisted rod-like particle assemblies. And so all that is opening in a simple aqueous solutions. You don't need to have complex, crazy solvents, which are also not very green and very expensive.
Yeah.
So I hope that answered your questions in details, but certainly I can continue.
We're going to move to our last question. Now it's from Sirikant Maladi. He
Mhm.
is a researcher in India.
Mhm.
Basically, a very nice talk. How electron spin polarization of nanoparticles help to induce chirality?
Electron spin polarization of nanoparticles. Yeah, that's it's something that is being investigated by a number of people. I state from my side that electron spin polarization in these particles is not something that we can identify as a driving force for complexity or driving factor for complexity. It may be embedded there and it may be used for a number of, say, the catalytic reactions or something else. So if you look at, for example, that porous particles that we used for photocatalysis, electron spin at the interfaces of zinc sulfide, which are modified by this peptide, is likely to be present. And some contribution of it may be here, and it's actually a very good system to investigate it. But what we also see that the molecular dynamics, which was done in collaboration with Hendrik Heinz from the University of Colorado, indicated that we have here the very strong another factor, which is adsorption of the substrate inside of those porous particles. And that's what drives the enantiomeric excess here to be that high. So spin polarization is likely to be a factor for the electron transport through these particle systems, but I did not see it yet as a factor which we can firmly identify in the supraparticles and in the complex structures that we investigate.
I think we don't have additional questions, and I'm not going to extend the say with additional questions. First, then I would like to thank all the participants that was here today. And then we're going to have our next webinar the next month. And I would like then to thank you very much, Professor Nicholas, for the wonderful talk and for the very, very deep discussions. And then end out to try to make the complexity more simple for us to understand and realize what can be done using the parameters like chirality as a tool to assess the new chemistry, especially for the development of new energies. Okay. Thank you very much for everyone to be here. Thanks.
Thank you. It's a pleasure. Have a great Thursday.
Marcelo can close it.